Last time we talked about hypothesis testing in the context of the Z-testing. That is where the test statistic was a Z statistic. And that is appropriate when you're comparing one group with one other group and N is large. What we're going to do today is look at T-testing. And T-testing is again appropriate where you are comparing one group with another group, but N is small. There are two forms of T-testing. There is a correlated T-test and an uncorrelated T-test. And we're going to look only at the uncorrelated T-test. Let me, however, explain both of these circumstances. You can compare one group with another group when you're comparing a group at time 1 with the group's performance at time 2. Right? That is, if we measured arithmetic ability in a particular group at time 1 and introduced some treatment to that group and evaluated them at time 2, we would have the scores from group 1, which would result in X bar 1 and S1 and so forth, and we would have the group statistics including X bar 2 from time 2. Do you understand that the responses at time 1 are not independent of the responses at time 2? That is, they're correlated. Because people who score high, students who score high at time 1, that is, students who have high initial arithmetic ability, are likely to score high at time 2. The arithmetic ability is not suddenly going to disappear. Likewise, people who score low at time 1 are likely to score relatively low at time 2. That is, their arithmetic ability is not going to change drastically over the time period either. Arithmetic ability is seen to be a relatively stable skill, a stable attribute. So that this situation, that is a situation in which you compare a group at time 1 with the same group at time 2, is an example of a situation in which the appropriate test is a correlated T-test, at least if N is small. And let's assume from now on, or for the purposes of the current discussion, that N is small. Likewise, we could have group 1 at time 1 and group 2 at time 1. And we could match these people, or people in the two groups in some way. For example, if we were interested in the extent to which persons liked candy bar A and the extent to which they liked candy bar B, we could match people on their general liking for candy or candy bars. That is, we could administer a test, perhaps a pencil and paper test, in which we assessed people's general liking for candy bars. And then we could randomly assign one of those, of each pair, subject 1 to candy bar A, subject 2 to candy bar B. That is, we could take two people who had achieved the same score on our general test of liking for candy bars and have one of them evaluate candy bar A and the other candy bar B. And we could establish pairs in this way and assign one of the pair to candy bar A and the other to candy bar B. And you would again generate two sets of statistics, one associated with candy bar A and one associated with candy bar B. That is, we'd have two means to compare again. And if n was small, the appropriate way of conducting this test would be again a t-test, and more specifically a correlated t-test. Correlated because we've matched individuals. We've matched them on some critical variable, like general liking for candy bars, so that if two people both have a high general liking for candy bars, they should rate the candy bar they taste, whether it be A or B, relatively high. If we match two people who have relatively low liking for candy bars in general, then regardless of the candy bar they evaluate, their ratings should be much lower. So when you're dealing with either the same people across time or matched pairs at the same point in time, the appropriate version of a t-test to use is a correlated t-test. Are there any questions? We're not going to look in any more detail at either of these situations. We instead are going to look at a situation in which persons are assigned, often randomly, to either group 1 or to group 2. And I say apparently randomly. If we were interested in candy bars, again, candy bar A and candy bar B, rather than match people, would you agree we could simply randomly assign people to one group or the other? And we might assign subject 1 to group 1 and subject 2 to group 2 and so on. In this instance, because these pairs have not been matched on some critical variable, the response provided by subject 1 is independent of the response provided by subject 2. That is, it's uncorrelated with the response provided by subject 2. This is a situation in which persons are randomly assigned. There are other situations in which an uncorrelated t-test is appropriate. For example, if we were comparing the SAT scores, SAT verbal scores of males and females, we would have males in one group and females in the other group. And would you agree that the score achieved by any male is independent of the score achieved by any female? It's uncorrelated. Did I start cycling too fast, or is this so obvious that you've got in front of me? You're still drafting. That's good. Yes.
So are they uncorrelated because it's male and female?
They're uncorrelated because there's no relationship between persons in one group and persons in the other. If you have the same persons in group 1 and in group 2, that is, you measure people over time, then those responses are correlated. If you're interested, if you have a group of people with high blood pressure, you agree there will be variance in those group scores. Just asking for feedback. I'm here for you, not for me. There will be variance in those groups, in those scores. That is, some people will have extremely high blood pressure, some will have high blood pressure, some moderately high blood pressure, and so on. You then provide a medication to each of them. The result of that medication is not going to be that the people who had extremely high blood pressure at time 1 have extremely low blood pressure at time 2. And even if they do have low blood pressure at time 2, the persons who started with a lower blood pressure should have an even lower blood pressure at time 2. So the responses are correlated. Correlated obviously because you're measuring essentially each person with themselves. Responses are also correlated when you match people on some critical variable. Because this is using an individual, measuring an individual against that individual's surrogate, where you've matched them in some way, clearly leads to a situation in which the responses of person 1 are correlated with the responses of person 2. A quite different situation is where you randomly assign people to either group 1 or to group 2. A variation on that theme is where you assign males to group 1 and females to group 2 because you're testing for some gender effect. If I did that in this class and looked at responses on the first exam, your score should be uncorrelated with his score. Your score should be uncorrelated with his score because you acted independent of one another. And you were not matched on some critical variable that linked you in some extrinsic way. And we're going to look at situations in which persons are either randomly assigned in some classic way, or whether and situations in which people self-select into a group because of some personal attribute that is not shared by the other group, such as gender. When we looked at Z-testing, it was a 3-step process. Step 1 was, step 1, he said, now incredibly locked into something he doesn't understand. Step 1 was to establish the critical level of the test statistic Z. And in order to do that, we needed 2 pieces of information. We needed to know, first of all, the research hypothesis. We needed to know whether the research hypothesis posited difference or both difference and direction so that we could decide whether the test was 1 or 2-tailed. And we needed to know the level of alpha. Step 2 was to determine the obtained or observed value of the test statistic. And we did that by invoking a formula that links the 2 groups, the difference between the 2 groups as the numerator, and the standard deviation of the sampling distribution of sampling mean differences as the denominator. X bar 1 minus X bar 2 is the numerator, the square root of s1 squared divided by n1 minus 1 plus s2 squared divided by n2 minus 1 as the denominator. And we then evaluated the null hypothesis by comparing those two scores. And by evaluating the null hypothesis, I simply mean we decided that we would reject or fail to reject the null hypothesis. Are there any questions about this process of testing hypotheses? Let's then take an example of a situation in which n is small. A researcher predicts that persons' marital satisfaction differs as a function of whether they have or do not have children. No, let me. Okay. As a function of whether they do or do not have children. In order to test this hypothesis, the marital satisfaction of 62 randomly selected married persons is measured. 29 have no children and 33 have one child. So we have two groups. We have group 1 and we have group 2. Group 1 have no children and group 2 have one child. Before we go any further, should the test be one or two-tailed? The test should be two-tailed. Sorry, I put something wrong here, didn't I? We need to know the nature of the research hypothesis. The research hypothesis here was simply one of difference. That the marital satisfaction of persons will differ as a function of whether they have or do not have children. So it was a hypothesis simply of difference. Therefore, whatever test we conduct must be a two-tailed test. Let us presume that alpha is 0.05. I already know that I'm walking into a situation that we cannot manage, but we'll blunder on. You still need to know those two things to conduct a t-test. But you also need to know a third thing, and that is the degrees of freedom, represented as df, the degrees of freedom. As an aside, and you don't need to write this down because it won't be on an exam. You can write it down if it helps you understand something better. Degrees of freedom are the number of scores in a set that are free to vary. If you know that the mean of a set of 3 scores is 3, can you tell me the 3 scores? And the answer is no. Yeah, the scores could be 3, 3, and 3. The scores could be 0, 3, and 6. The scores could be almost an infinite variety of scores. If I tell you that the mean of 3 scores is 3 and that one of those scores is 0, can you tell me the other 2 scores? And the answer is no. Because the other 2 scores might be 3 and 6, they might be 4 and 5. You can't tell me. And there are other options too. If I tell you that the mean of a set of 3 scores is 3 and that 2 of those scores are 0 and 4, can you now tell me the third score? You can now tell me the third score. The third score must be 5. So in a group of 3 scores, 2 are free to vary if you know the mean. in general, in a group of n scores, n-1 scores are free to vary. So that the degrees of freedom ordinarily would be n-1. We have two groups here, however. Group 1, in which n is 29, and group 2, in which n is 33. n1 minus 1 then, so the degrees of freedom in this, n1 minus 1 is 28, plus n2 minus 1, which is 32, so that the total degrees of freedom are 60. Would you agree? Yeah? You can now decide the critical value of T. If you go to, actually you'll find you can't, but, and this is the cul-de-sac that we were always headed into. If you go to table C, table C is a table of T values. Across the top says level of significance alpha. But above that you'll see the diagram of the normal curve, and it indicates that if you're testing both for both positive and negative difference, that you have to divide alpha by 2. Yes? No? Anybody have a cell phone I can use? Book I can read? At the very top of the page, it reproduces for you a normal distribution, and it indicates two shaded areas, one at the positive end of the distribution and one at the negative end of the distribution. And associated with each indicates alpha over 2. What that indicates is that if you are conducting a two-tailed test and you're going to use this table, you have to divide alpha by 2. So I tell you what we'll do. Because if we divide alpha by 2, what we get is 0.05 divided by 2, which is 0.025. And if you look at table C, you'll see a series of alpha values. Working from the extreme right, 0.001, 0.01, 0.02, 0.05, 0.10, and 0.20. That is, there is no column here associated with alpha equal to 0.025, which is really useful. So, when it comes to the exam, you're not going to be able to answer half the questions. So don't worry. Be happy. What I will do is I will distribute a more complete table of T values for you. What we'll do so that we can use this table is we will change alpha from 0.05 to 0.02. we're conducting a two-tailed test. So we have to divide alpha and deploy it, half of it at the positive end of the distribution and half at the negative end of the distribution. So that the alpha value now becomes 0.01, would you agree? We then go from level of significance alpha to the column of scores headed 0.01. And the first score in that column is 63.657, would you agree? What we want to know now is which of the scores in that column is the one that we have interest in. And to decide that, we need to know the degrees of freedom. And the degrees of freedom in this study are 60. So that we go down the extreme left-hand column, headed DF, that is degrees of freedom, to 60, which is the third value from the bottom, and across to the column headed 0.01. And what we discover, would you agree, is that the critical value of T is plus and minus 2.66. Yes?
I have a question about how do we get from the alpha being 0.05 to searching for 0.01?
First of all, I arbitrarily changed the level of alpha because I'm the researcher from 0.05 to 0.02.
Okay, yeah, after that, what happens?
If you just sit back, pedal, it'll come out. Having changed alpha to 0.02, because we are conducting a two-tailed test, half of that alpha has to be deployed to test for negative difference, and half has to be deployed to test for positive difference. So that the level of alpha, in this instance, using this table, is 0.01. So we go to the column of values, t-values, headed 0.01. And then we use the degrees of freedom on the left-hand side, and that's 60 in this test, to identify the specific t value that is relevant to our study. And it turns out that the relevant t value, critical t value, is plus and minus 2.66. Does anybody not understand how, first of all, the pieces of information needed to determine a critical level of T, which is the more important issue here. The second issue is how to use table C. That's less important because you're not going to be using table C. You're going to be using a more complete T-table that I will distribute to you. So the primary issue here is, do you understand that the difference between determining a critical Z-score and determining a critical T-score is one piece of information? You simply need now to know the degrees of freedom, which is given by N1 minus 1 plus N2 minus 1, which equals N1 plus N2 minus 2. And since N1 plus N2 is the number of people in the study, we could rewrite this as uppercase N minus 2. There are two groups in the study, would you agree? People without children, people with children. If we use the letter K to denote the number of groups, then the degrees of freedom are given more generally by N minus K where n is the number of people in the study and k is the number of groups. But in this instance, you work it out any way you like. n1 plus n2 minus 2, or n1 minus 1 plus n2 minus 1. This piece down here is just thrown in because it will connect to something in the future. Are there any questions about the determination of a critical t-value?
I have a question. You said for 0.01, you said the 63.657. How do we deduce that? Maybe I was writing when you were talking about that.
This table says level of significance, parentheses, alpha. Yes? Alpha in this case is our original alpha, 0.02, divided by 2 because we're conducting a two-tailed test. So the level of significance, alpha, for this test is 0.01. So we're interested in the column of values under 0.01. And the first t-value there is 63.657. Would you agree? Well, in order to determine which value in this column is the value for our study, we need to know the degrees of freedom. And the degrees of freedom are listed on the extreme left, going from 1 to infinity. We have 60 degrees of freedom. So we go down the column headed 01 and across the row numbered 60, and they intersect to indicate that the critical t-value in this case is plus and minus 2.66.
So the number 63.657 isn't significant aside from the fact that it's under the column of 0.01.
Yeah, I was just identifying which column of t-scores we were interested in. I would direct your attention to when the degrees of freedom are infinity. If you look across there, a two-tailed test with alpha equal to 0.05, the critical value is 1.96, which should be recognizable to you as the critical value when we were using Z and not T. We now need to decide on or compute the obtained value of t. And we do that by invoking the same formula that we use to compute z. That is x bar 1 minus x bar 2 divided by the square root of s1 squared divided by n1 minus 1 plus s2 squared divided by n2 minus 1. Let us assume that the marital satisfaction of the 29 people with no children, that is x bar 1, is 7.46. And that the standard deviation of those scores is 1.89. Let's assume that the average marital satisfaction of people with one child is 6.16, and that the standard deviation of those scores is 2.04. Would you agree that we can now plug and chug? That is, x bar 1 is 7.46. minus x bar 2, which is 6.16, divided by the square root of 1.89 squared, divided by n1 minus 1, which is 28, plus 2.04 squared, divided by n2 minus 1, which is 32. Are there any questions as to how we got here? There are no questions. So what is the obtained value? Of t? Because I know I computed it wrong last time, so I'm out of the computation game. The numerator here is 1.3 divided by the square root of about 8 over 30, something like that. I'd guess somewhere about 3.2. 2.6? Did we have a second 2.6? 2.6? Okay. The observed value of t, or the obtained value of t, is 2.6. Let's assume that the critical value is plus and minus 2.66. What do you conclude? Pardon? Well, they're not the same. One is a fraction larger than the other. So do you conclude that the marital satisfaction of people with children or with no children differs from the marital satisfaction of people with children? Or do you conclude that there is no significant difference between the marital satisfaction of people with and without children? Okay. It doesn't depend. It doesn't depend. At this stage, it doesn't depend.
Well, since it has a plus or a minus, does that mean that it does depend? I mean, it doesn't depend, but that it does if the level is different?
No, no. I don't. Let's get rid of all of this. We have a sampling distribution of sample mean differences. That distribution is normal. That's what central limit theorem told us. In this instance, because we're dealing with a sampling distribution of sample mean differences, we're dealing with values of x bar 1 minus x bar 2. So at the center of this distribution is the circumstance where the difference between x bar 1 and x bar 2, the difference is 0. To the extent that we depart from 0 towards the positive end of the distribution, that indicates that x bar 1 exceeds x bar 2. To the extent that we depart towards the negative end of the distribution, that indicates that x bar 1 is less than x bar 2. Well, we know from the data that x bar 1 is greater than x bar 2. So our attention is focused on this side of the distribution. The hypothesis, the research hypothesis, was that the marital satisfaction of people with children will differ to the marital satisfaction of people with no children. Yes? That is, we had to test for both negative difference and we had to test for positive difference. The necessary step in there was to determine how many standard deviations we had to go away from the mean to exceed some critical value. That is, we had to decide on the critical value. And in this instance, we decided that the critical value was minus 2.66 standard deviations and plus 2.66 standard deviations. Do you agree? Let me ask, is there anybody who's sitting there going, I don't get this? What we've decided is that if the obtained or observed value of t is not in one shaded region or the other, that is, if it's in this region, we will fail to reject the null hypothesis. If it's in this shaded region, we will reject the null hypothesis. We've got a Quasimodo. We've got an elephant man. If it's in this shaded region, we will reject the null hypothesis. We've got Leonardo DiCaprio, or whomever. Some guy on Grey's Anatomy, she told me. Yeah. Our obtained value of t was fractionally below the critical value on the positive end of the distribution. I'm assuming that it's 2.60. It doesn't matter. It doesn't matter. On this basis, do we reject the null hypothesis or do we fail to reject the null hypothesis? We fail to reject the null hypothesis. We therefore conclude that there is no significant difference between the marital satisfaction of people with children and the marital satisfaction of people without children. Is there anybody who, first of all, does not understand how to determine a critical value of t, or at least does not understand the pieces of information that you need to be given in order to determine a critical value of t? Are there any questions regarding the computation of an obtained or observed value of t? Are there any questions about evaluating the null hypothesis? This means first being able to say to yourself, we reject the null hypothesis or we fail to reject the null hypothesis. In this instance, it also means, second, that you be able to cast that decision in terms of the problem that you're faced with. That is, in terms of the relationship between the marital satisfaction of people with children and the marital satisfaction of people without children. In this case, we failed to reject the null hypothesis. What that means is we concluded that there was no significant difference between the marital satisfaction of people with children and the marital satisfaction of people without children. And you need to be able to take that last step. That is, you need to be able to go beyond we reject the null hypothesis or we fail to reject the null hypothesis. You have to be able to cast that decision in terms of the problem that you're confronted with or the situation that you're confronted with.
So would we have failed? Would we have rejected it if it would have fallen to the two sides, the shading?
Let's assume, and this is why I say the computation and the numbers are in some respects irrelevant. They're relevant when you get to an exam, and we'll focus more closely on them. But at this stage, what's much more relevant is that you understand the process. So let's assume that the obtained value of t was plus 4.26. That is somewhere down here. If that is the case, if that had been the case, would we A, reject the null hypothesis, or B, fail to reject the null hypothesis? We would have rejected the null hypothesis. I will ask, anybody who does not understand why we would have rejected the null hypothesis? Would anybody care to cast that decision the marital satisfaction of people with children?
There is significant difference between married people with children and married people without children.
There is a significant difference in the marital satisfaction of people with children and people without children. We would conclude that there is a significant difference in the marital satisfaction of people with children and people without children. I'm back. I just went for walkabout. Now I've got to say all that again. I don't know where I lost sound. You didn't miss anything important. We've just been playing Monopoly, sitting around the campfire singing songs. Are there any questions?
Can you just explain one more time? Because where I get lost is how can you tell if it's a one-tailed or a two-tailed?
Okay. Your question.
I'm still kind of lost with the alpha changing to point.
Okay. Let's not bother ourselves with scores. Let's assume that we have hypothesized that females will score significantly higher than males on the verbal section of the SAT. So what we do is we collect together some number of females, some number of males. We sample from a population of males and females. We secure the females' verbal scores, the males' verbal scores. We compute means for the two groups and standard deviations for the two groups. Yes? And let's assume that n is small. Should the test be one-tailed or two-tailed? What is the research hypothesis? What is the predicted relationship between X bar 1 and X bar 2, where group 1 is a group of females and group 2 is a group of males? You only got three choices here. X bar 1 will be greater than X bar 2, X bar 1 will be less than X bar 2, or X bar 1 will be different from X bar 2. The hypothesis was, or the prediction was, that females will score higher on the SAT than males. Surely what the researcher is predicting is positive difference. So, should the test be one or two-tailed? The test should be one-tailed because you only have to test for positive difference. You don't have to test for negative difference. Let's suppose that there are 25 females in group 1 and 22 males in group 2. Let's assume alpha is 0.05. How many degrees of freedom are there? Are there 47 degrees of freedom? Are there 45 degrees of freedom? Are there 1107 degrees of freedom? Or are there no degrees of freedom? Or are there just bags of degrees of freedom? I'd say 45. N1 plus N2 minus 2, which is 47 minus 2. If there, I saw a hand go up. I'm now gun shy. You know, unless you're going to make some positive response, you smile, that would be good. Applauding would probably be too loud, it would shock me. If you want to nod your head, that's good. Would you agree that one way or another, a week from now, maybe, you will be able to combine these three pieces of information to determine a critical value of T? The second step here is to decide or compute an obtained value of T. And you do that by using the same formula that you use to compute Z. So that should be no problem at all. Let's presume that in this instance the critical value of T is plus 1.814. Oh, I'm colouring it. And as usual, I'm not colouring within the lines. That was always the comment on my drawings. This would look a lot better if you coloured inside the lines. Well, yeah, so would you if you coloured with inside. We have this sampling distribution of sample mean differences. What we have done here is to establish some critical region. A critical region that exists beyond 1.814 standard deviations above the mean. If the obtained value falls in this area, we will reject the null hypothesis. If it falls in this area, we will fail to reject the null hypothesis. Agreed? Let's assume that the obtained value of T is plus 2.06. All those who say the null hypothesis, legions of them, how many would say we fail to reject the null hypothesis? How many say I do not know? You all got that right. And I think I deserve a salary increase. You would reject the null hypothesis. You would conclude what? Would you conclude that females scored significantly higher on the SAT than males? Or would you make some other conclusion? Some other conclusion? No. You would conclude that females scored significantly higher on the SAT than males. That was the research hypothesis. You have rejected the null hypothesis in favor of the research hypothesis, so that you would conclude that indeed female students score higher on the SAT verbal section than male students. Read over the material. This process, if you haven't discovered it already, is monotonous. Because no matter where you start from, you're always undertaking the same process. Determining a critical value of a test statistic, computing an obtained value of the test statistic, and using those two scores to evaluate the null hypothesis. The only difference between a z-test, the information needed for a z-test, and the information needed for a t-test is that you now need, because we're dealing with small samples when t-testing, you need to know the number of degrees of freedom, which is tied to what? It's tied to sample size. Okay. We'll go on with this discussion next time.